Hello everyone, welcome back to Lecture 2 in our Arrhythmias review. This video is going to focus on cardiac action potentials. So if you remember in our last video, we went over EKG basics, how an EKG is produced, and the electrical activity that leads to that EKG. And in this video, we're going to take a look at the actual action potentials themselves, the ion concentrations that can affect these action potentials and that are responsible for the phases of these action potentials. And then just to give us an idea of how different drugs may modify these action potentials. So let's get started. The first action potential that we're going to look at today is generated in these two structures that are highlighted in purple over here on the heart, which are, if you remember, the SA node and the AV node. Here you'll see the action potentials that we're talking about, and because these are made in the SA node and AV node, they are referred to as the pacemaker potential. Now, looking at these action potentials, something interesting you may notice right over here and right over here on each of these two action potentials is the ability of this tissue to depolarize, spontaneously depolarize itself. So as you see right here, the cell is below the threshold, currently not generating any action potential. And there's a little current here that is referred to as, quite literally, the funny current that is active right here, that once the cell reaches its most negative point, once it is hyperpolarized here at the beginning of the action potential, this current, the funny current, will kick in and cause this cell to breach the threshold and spontaneously depolarize, thus giving the cell the ability to produce action potential without any input. Once the funny current has caused the cell to breach the threshold, a different type of channel will open up, known as the calcium channel. Now, this is very important to remember, as the calcium channel is mostly responsible for this phase 0 depolarization here on the action potential. This is something that is unique to the pacemaker cells that other cardiac cells do not have. So once the cell has depolarized, it has gone and reached its most positive point. It, of course, does need to repolarize before it can then fire again. At this point, it's fairly similar to what we'll see later, but you will now see the potassium channels open. And the potassium channels are responsible for this phase 3 repolarization back down below the threshold and eventually back to a hyperpolarized state. Just as a quick review of what we've just talked about, once it reaches this hyperpolarized state, the funny channel will kick in, causing the cell to breach the threshold. Calcium channels will open, the cell will become more and more positive, and then potassium channels will open, and the cell's membrane potential will go back to hyperpolarized and negative. Another interesting note that is important to remember in this section is that while both the SA node here and AV node can produce these action potentials on their own, the rate at which each of these triggers action potentials is different. So in the heart, whatever tissue is producing the fastest action potential, we will write this out here, tissue producing the fastest pacemaker potential sets the heart rate. So what does this look like in real life? Over here, as we know, up here in the SA node is generally where our pacemaker potential happens. This is because the AV node, as we talked about in the EKG basics, tends to hold on to that electrical activity a little bit more, and its intrinsic rate is slightly lower at about 40 to 60 beats per minute. And then, as we know, up here in the SA node, a normal heart rate is generally considered between 60 to 100 beats per minute. As we talked about down here, with the fastest depolarizations controlling the heart rate, in this situation, the SA node will win out over the AV node, and the heart rate will be a little bit closer to the 60 to 100 range. That can change with some types of arrhythmia, but we will reach that in some future lectures. The next action potential we need to talk about is this one right here. And down here in the bottom right, we do have the pacemaker potential just for you to compare it to. But this next action potential is referred to as the fast action potential. And this action potential is found in the rest of the myocardium. So as we talked about, pacemaker potential comes from the SA and AV node, but this fast action potential is in the rest of the myocardium. This has a few more steps than our last action potential with some different ions. So we're going to go step by step and review each of those. So the first phase we're going to label here briefly is phase 4. The time right here when no action potential is being generated in the tissue. This is resting membrane potential. So at point 4, the membrane is at its most negative point. Unlike the pacemaker potential, the fast action potential does not have the ability to depolarize spontaneously. So at this point, the cell's membrane has depolarized just enough to allow the next ion channel to open, which is sodium channels. So this is a big difference I do want you to remember. For this, as we refer to it, phase 0 depolarization, this is controlled by sodium channels. As we remember, during this same phase 0 depolarization, over here in the pacemaker potential, this was controlled by what? Calcium. So this is the major distinction between the pacemaker potential and the fast action potential, is that sodium is responsible for this phase 0 depolarization. The next piece of this action potential that we need to talk about is this plateau phase. So once the cell has depolarized, it's gone up and it has become its most positive. At this point, we will see a slight repolarization, as we see right here. The cell becomes ever so slightly more negative, and this is what we refer to as the phase 1. This is the initial repolarization. Once this initial repolarization has taken place, another ion channel will open, which is responsible for this part of the action potential, this plateau phase. And that next channel is the calcium channel. Calcium channels here are responsible for phase 2, or the plateau. So during this phase, calcium is moving into the cell, both keeping the cell positive and, more importantly, helping the cardiac tissue to contract. We won't do a full review of how calcium influx into a cell helps the tissue to react, so I suggest you go back to previous course materials or other online materials to find that out. But during this period, calcium influx into the cell is causing muscle contraction, helping the blood, helping the heart or the myocardium to pump blood to the rest of the body. For the next phase, we do see a repolarization, and during this phase, again, potassium channels are active. So this is something that is interesting to note. While the initial phase 0 depolarization in the fast action potential and the pacemaker are controlled by different ions, repolarization phase in both action potentials is governed by the same ion, and that is potassium. And during this phase, this is referred to as phase 3 of the action potential, which is repolarization. Of course, once the cell completely repolarizes, we go back to stage 4, which is the resting membrane potential. And for completeness sake, we'll add in here phase 0, the depolarization. So just running through this all one more time, because this is very important to remember, especially when it comes to our drug therapy and how different drugs will affect this action potential. Initially, phase 4, resting membrane potential, the cell is the most negative. Nothing is happening in the cell. It does not produce its own depolarization like the pacemaker potential. But at this point, due to changes in voltage, a voltage-gated sodium channel will open. This is phase 0 depolarization, causing the cell to depolarize and become more positive. Once the cell is fully depolarized, it will undergo an initial repolarization here, and this is phase 1, and then calcium channels will open, causing phase 2, this plateau, as calcium rushes into the cells and helps the cardiac myocytes contract. Once this phase is started to wrap up, potassium channels will open. This is phase 3, repolarizing the cell, just as we see potassium do in the pacemaker potential, back down to 4, the resting membrane potential. The next thing we're going to do is we're going to take this fast action potential that we've just learned, and we are going to overlay it with an EKG, just so that we can see how this action potential relates to what we are currently seeing on an EKG. So for this example, we are going to be looking at this action potential as it comes from down here in the ventricles, the lower chamber of the heart, and how that would line up with the EKG. So the first thing we're going to see as the ventricles start to depolarize and the middle septum is being depolarized is the Q wave. Of course, shortly thereafter, the Q wave is followed by the rest of your QRS complex as the signal then travels down towards the recording electrode. Mind you, this is in lead 2, I should specify. And then eventually circles back up, giving us our S wave. So we'll get the full QRS complex. After this point, during this plateau that we talked about, when calcium is fluxing into the cells and causing contraction, giving the blood time to pump out of the heart, at this point is when everything is depolarized in the heart. The entire cardiac tissue here is going to be positive at this point. As we said in our EKG video, this means that there is no net movement of ions in the heart at this time, so this is where we will see our first little bit, the ST segment, with no movement. We'll see just a flat line as the entire myocardium is depolarized. As we also talked about in our EKG basics video, the next phase, this repolarization phase of the action potential, is when this depolarized membrane starts to repolarize itself in the opposite direction than it came. So this will no longer be positive, and we'll start to see it repolarizing back to its negative potential. As we have negative charges moving back up towards our negative electrode that is up here in lead 2, we of course see a positive deflection, giving us our T wave. This is of course not perfectly drawn to scale, but this should give you an idea of how both of these line up. Important things to remember is this initial depolarization is where we see our QRS complex. The flat line afterward, as everything is depolarized, is here in the action potential while everything is depolarized and calcium is fluxing into the cell, causing muscle contraction. And then here, repolarization governed by the potassium is what's going to give us our T wave here. Now that we've reviewed both the fast action potential and the pacemaker potential and their differences, which ions govern their shape, let's take a look at some medications and see how those medications may affect these action potentials and therein how they may treat some arrhythmias. So I will see you all back in lecture 3 on antiarrhythmic drugs.